Hello, everyone, and welcome to the SciRoc camp. Hi there, my name is Deebul Nair, and I'll be your host for the SciRoc camp. So, the SciRoc camp. The SciRoc camp is an effort under the SciRoc project to train and develop new robotics team to participate in different robotics competitions and different benchmarks all across the world. So there are different robotics competitions like the Smart City event, SciRoc, and the European Robotics League and Robocop. It's an effort to bring up teams so that they can easily participate in these competitions. So today we are on the third day of the camp. On the first day, we started with the Champions Talk. We had two top teams, Team SciRoc from Portugal and Team Bitbots from Germany. They shared their experiences and how they participate, which will be useful for the teams to know how it goes in these robotics competitions. After which we moved on to the tutorial series, and we had the first tutorial, the perception tutorial in robotics by Mohammed Wazir. And today we continue with our tutorial series. Today, to deliver the tutorial on robot task planning, we have Oscar Lima. Yeah. So Oscar Lima did his engineering in mechatronics from Facultad de Ingeniería de la UNAM, Mexico. After which, he did his master's in autonomous systems, Hochschule Bonn-Rhein-Sieg, Germany. Currently, he's working as a researcher in the Plan-Based Robot Control Group at DFKI, which is the German Research Center for Artificial Intelligence in Osnabrück, Niedersachsen, Germany. In addition, he's also pursuing his PhD in human-aware, robust execution of plans in service domestic robots from the Instituto Superior Técnico Lisbon, Portugal. He has a vast experience in the field of robotics benchmarking and robotics competition. He was active member of the Team Bitbots and then in Team SciRoc. I vividly remember him how Oscar was pivotal in upgrading the planning of Team Bitbots, which was from state machine to a planning-based, ROSPlan-based methodology, which eventually was also his thesis topic. Today in this tutorial, he will demystify the subject of robot planning by providing a clear overall picture of where and how the planning is, and basically how ROSPlan fits into this picture. So let me welcome Oscar Lima. Hi, Oscar. Welcome to SciRoc Camp.
Hi, Deebul. How are you?
Good, thank you. I'm good. So, what do you think about the SciRoc Camp in overall? Let me get your views before we start with your talk. Oscar, can you hear me? Oscar, can you hear me? Hi, Oscar. I think we are facing some difficulties. Let me check with him again. Hi, Oscar. Hey, hi, you're back.
Hello.
We just lost you for a moment. So I was asking you, what are your thoughts on the SciRoc Camp before we start with the talk?
Okay. Yeah, I think it's a great opportunity for us to interact and to share some ideas. I mean, especially during these difficult times,
Yes.
having the possibility to do this remotely is, I think, fantastic.
Yeah, so I think that's the very most important thing what we want to do even in this time, to remotely to connect with most of the researchers in there and to listen to their thoughts. So I think now you can share your screen. That will be a right moment to switch on to move on to the talk. But before we go on to the talk, just a final comment to the viewers. We are streaming live on YouTube. So if you want to ask anything to Oscar about the planning tutorial, you can ask in the YouTube chats. And it should be available we can ask him after the talk. So,
Hi.
Oscar, hi. So, can you share your screen now?
Oh, yeah. Is it there?
Yeah, one sec. There you are.
Oh, nice. So then I start now, okay?
Yes, it's up to you.
Okay. Yeah, so I will give a small talk about planning in robotics in general. It's not entirely from a practical perspective, so it has also some concepts, some basics on planning, and also some research directions on the talk. So the contents of this lecture are introduction, background, formalization. Then we will talk a little bit about PDL, the planning domain definition language, some of the planning formalisms that exist, and something about plan execution, which is probably the most interesting part. I will spend more time there. Also some trends in task planning from the research perspective. And we'll finish with some scientific venues for task planning. So we started introduction, and I would like to mention especially this book, which is highly relevant for planning. So this is like the planning Bible, and it's typically used in the planning lectures as a main textbook. So the motivation behind planning. So what problem does it solve, or what is it used for? So planning is explicit offline deliberation process, and you can use planning to choose and organize actions by anticipating their outcomes. So you do this by creating a model of the domain, but we will see that a bit later. So it's useful to do some sort of decision making. And one way to do this is to decompose high-level goals into more detailed sequence of actions that, when followed correctly, the robot will solve a goal. So this is, for example, in robotics, you will have your robot in front of you and you will tell him, bring me a Coke. And then this means that the robot will needs to first move from that position to the kitchen, maybe, then perceive the counter to see if there is a Coke, then grasp the Coke, then drive back to you, and then hand over the Coke to you. So this is how a plan usually looks like. And in a nutshell, so task planning is useful for decision making in robotics. It's intuitive for humans. So we will see some other decision making approaches which are perhaps not so intuitive for humans. So the claim is that task planning is intuitive for humans. And it's also a mature and well-established research area. So the objectives of this tutorial, so because task planning can be a course on its own, and it's too big to be covered in a 45-minute session. So our aim is just to give an introduction and a big picture in the context of robotics, and also to get you a little bit interested into the topic, cover the basics and an overview of the field from a research perspective. And we'll also talk about the ROSPlan and plan execution. So first, I would like to make you aware of the fact that task planning was not made for robotics. So robotics is just a small part of planning. And in general, task planning is a generic tool for problem solving. And these problems are across multiple domains. So there is the logistics domain, the white-collar hacking domain. So there are planners constantly hacking systems to see if they have some weaknesses. It's also used in the oil extraction business in robotics, but it has like hundreds of applications. And the main message is that it's not specifically made for robotics. We are using it for robots, but many other domains as well. And then we have planning as a search process. So we will see that later, but we have domain-independent heuristics and we have domain-dependent heuristics. So this will sort of like make a planner to search faster through the search space in a generic manner. So this is domain-independent or tied to a specific domain that you know, specific heuristics about it. So a little bit of the background. So what are our options? So we have task planning, but we can also do other things. So typically, the most popular way of doing decision making in robotics is with finite state machines. So finite state machines are easy when they are small, and if they grow, they become very hard to maintain and very hard to extend. And although some new approaches are trying to make them hierarchical. So when you have hierarchical state machines, things become slightly better, but still it is a very handcrafted way to do decision making. And in our case, I mean, when we were in the competition, we were doing everything with state machines at first, and it was very, very complicated after a while because the state machines were huge. But in theory, there is nothing wrong with state machines, and in theory, they could solve every single one of your problems with a gigantic state machine, let's say. So another way you can do decision making in robotics is with Petri nets. So Petri nets, it's this sort of like a net that you have tokens, you have placeholders for the tokens, and somehow you have this living mechanism that passes tokens from one place to the other. And as it reaches a particular placeholder, then you trigger actions. In this case, this Petrinet is solving a problem for the Robocop at home competition, which is to assist Granny Annie with a vacuum cleaner, and you're waiting also for some technician which could ring the bell and so on. So another way to do decision making in robotics is with behavior trees. So these were developed in the computer game industry, and they describe the behaviors in modules. And one nice thing about behavior trees is that you have a model of failures. So if something goes wrong, just take the left part of the tree. If not, then continue to the right. And then you can sort of go and traverse the tree, and you can make the robot to follow the behavior that you want. So behaviors are composed of sub-behaviors. So there is hierarchy, there is task competition, and they are also extensively used by CMU. And in this case, this behavior tree is encoding the task to move the green cube to the goal location with the U-bot. Another way that you can make decision-making robotics is with reinforcement learning. So reinforcement learning, it's actually nice because it works in the MDP framework. So it works with Markov decision process. So this means that the action, the outcome of the action of a robot can be non-deterministic. So now you have a probability of this action being successful, or a probability of this action being not successful, and then you have a policy that essentially maps states into actions. So if I am in this state, what should I do? And the objective is to learn that policy. So for each state, to know what to do. And there are some interesting research going out, like AlphaGo. It's using a deep reinforcement learning. And I just don't want to go much into details, just to let you know that there are multiple alternatives to task planning. But finally, in task planning, so it's also called by other names. So task planning is also called sometimes automated planning and scheduling, or AI planning, or activity planning. And what task planning is, it's a branch of artificial intelligence that deals with decision making at a high level. So this high level part, I mean, you can combine task planning with other things. You can combine task planning with behavior trees or with state machines, and where the actions of task planning can be one state machine on its own. So we have a planning problem, and basically we are going to solve this problem via search, but we will see that later. So it's important to do the remark that classical planning does not involve artificial neural networks, but there are some researchers currently looking into it and working in the intersection of neural networks and task planning. So this is a hot area of research now. And it all started in 1971 with the Shaky robot and the Strips planner at Stanford Research Institute. And since then, it has evolved into the ADL, the Action Description Language, and then PDDL, and furthermore. But yeah, we'll see a bit more of that later. So basically, in task planning, what you have is you have a domain, which is a description of the world and your agent and how do they interact with each other. You have a problem instance, which is the particular goal that you want to solve at that time. And then a solver or a planner will take these two inputs, and then it will produce a plan. And then this plan you need to send for the robot to execute. So finally, you have another way of doing decision making, which is reasoning. So reasoning is implemented. One implementation is available in NOROP framework. And in reasoning, what you have is basically the following premise. So the robots will not change much in the next years. So they will more or less have the same motors, the same sensors, and the same capabilities, such as pick and place and perceive stuff. And there is really no need to plan all the time. So you can just make like a template plan and then adapt this hard-coded plan to particular environments, different environments and different robots. So reasoning is encoding knowledge of the domain in an ontology, and is trying to ground these to a particular problem that you have at hand. So yeah, I mean, task planning builds on top of propositional logic, first order logic, and temporal logic, probability theory. So it is nice to have this table here to see what are the relations with each other. So in classical planning, you have propositional logic, which means that the facts in the world are either true, false, or unknown. While in probability, you have a certain degree of belief of the fact. So the facts in your knowledge base would have a probability from 0 to 1 of being true or being false. And then the agent will have to take decisions based on that. And in fuzzy logic, you have the facts have also a certain degree of true, but the interval value is known. So now we will go very, very quickly through the task plan formalization. So this is something that you would see in a planning course, but here we will just quickly rush through it because it's important for some concepts that we will talk later. So first of all, and this is a very nice slide, I have to say, because these are the assumptions of classical planning. And the assumptions comes with the limitations of the system. So in classical planning, you assume that you have a discrete representation of the environment, but what we really have in real life and in robotics is a continuous representation of the world. So in task planning, in classical planning, you have like episodes. So everything happens like you can think of it like as a snapshot of the world. And then you have that actions are instantaneous and they take no amount of time. They are just instantaneous actions. This assumption is removed in a different branch of planning, which is called temporal planning. So in temporal planning, you have some model of the time, and you have duration of the actions, and you can play around with deadlines and handle time. Then in classical planning, you have sequential plans, but what we really need is concurrent plans in robotics. You have a fully observable world, so you can see everything in the world at all time. But really, I mean, the reality, you have partially observability. So you cannot observe everything at the same time, unless you have a camera somewhere. But usually that would be like expensive. And the action in your agent. So in classical planning, when you execute an action, it will always succeed. But in reality, this is false. I mean, sometimes if you execute the same actions 50 times, then maybe 45 times you will succeed and 5 times you will fail. And so what we have here is a stochastic action outcome. And this is what you have in reality, but in classical planning, you have the assumption that everything is deterministic. And you have goal state conditions that you can give as a goal for the planner to solve. But in real life, what you really have is temporal goals, so goals with deadlines. You have preferences over certain behaviors over another ones. You have certain rewards at the end of a certain process. Or you just have like a sequence of tasks that you want the robot to achieve, which is actually addressed in HTM planning. Yeah, so why do we do all of these assumptions? Because then classical planning becomes complete, p-space complete, so it became searchable in polynomial time, and then you can solve the problem. Otherwise, the search will take years or even decades. So yeah, so just some very general concepts in planning. So grounding is the process of substituting a variable with an instance. So in this case, it can be grounding a predicate or grounding an operator. Grounding a predicate means, for instance, that robot is at certain location. The grounded would be robot is at the kitchen. And the operator is another is an uninstantiated action in the planning world. So an operator is more or less like a recipe, and when you ground, it will become an action. So this will be something like move from location A to location B, and the action would be move from the kitchen to the living room. And then in planning, all the building blocks in planning are actually predicates. If you remember, a predicate is an uninstantiated fact. So a predicate or a fact is nothing but a vector of literals. So here you have the example, which is ungrounded and grounded. So the ungrounded is the robot is at a certain location, and grounded is the robot. The robot is at a platform S4 in this case. And then what you have in planning is different ways of representing the search. So you have one way of representing the state is just as a collection of facts. So you will need a knowledge base for that to store those facts. And then the state S1 here is represented as a picture, but you can, in planning, this is just a collection of facts, like robot is at location 2, the pallet is at location 1, the crane is holding the container, and such things. And then a plan is just a set of actions with some constraints that the robot needs to execute in order to transition from one state to another. And so we already talked about what is a state. So here, two important states are the initial state and the goal state. So where are you now and where you want to go. And a goal is, it's a state, so it's a collection of facts, but it's a subset of a larger set of facts that you want to become true. Yeah. So the operator we already explained. So these are the actions that the robot can do. And here is some example. So you have the action, the operator move. So move a robot from a source to a destination. And a grounded operator would be like move the Roomba from room A to room B. And then you have actions which are applicable. So actions which are applicable, an action is applicable in state S is if all of its preconditions are met. And what are the preconditions? Preconditions are facts that you need to be true in that particular state. And then applicability is important because this is basically how you will grow your search tree in planning. So preconditions, facts that must be true in the present in the knowledge base. So they have to be in the knowledge base as part of the states. And you can also have negative preconditions. So you can have some facts that must be false. So a fact being false means that it's not in the knowledge base or it's not part of the state. And here you have the example that if you have a Roomba, 2 rooms, so the action is clean. The parameters is that the robot is at a particular location. The precondition is that robot is at that particular location, that location is not clean. So this operator becomes applicable if and only if the robot is if the room is dirty. And the effects is basically facts that will be added to knowledge base after you execute an action. And you can also have negative effects, which are facts that are deleted from the knowledge base. And finally, you have some function that will make the transition between states. So if you apply action A, the robot will switch from this state to the next one. And now that we have all the ingredients that we need for planning at the conceptual level, so we have here an example of how this planning domain would look like. So this is what you will have to write. If you want to use task planning in robotics, you have to model the domain as a domain expert, and this is how it would look like in PDL syntax. So task planning representations. So here, I don't want to go much into detail, but just to make you aware that there are different ways of representing the graph in planning. So you have the first way is the one that we already described, which is a state space. So the nodes are the world states, which are collections of facts, and each edge represents a state transition. And but you have other ways of constructing the graph, the search graph, and this is plan space, where the nodes are partial plans and the edges are plan refinement operations. In general, plan space is more efficient than state space planning. But in reality, because in state space we have very, very nice heuristics nowadays, then in reality, state space is more used than plan space planning. And finally, you have task networks, or HTN, where the nodes are primitive operators or methods, and the edges are represent ordering constraints. So basically, the idea is that once you have constructed your search space, your graph, now what you need to do is apply standard search algorithms like best breadth first search, depth first search, or A star. The problem here is that these planning graphs are usually very, very large. And so in practice, you cannot use best first search to search such a problem, because first of all, you will not have an optimal solution or a good solution, but it will also be likely to be very slow. And but just as a concept for you to understand that the task planning is basically search in the background with some heuristics or with some technique that allows you to search faster through the space. And the path in the search space corresponds to the plan. And here we have some very basic search algorithms, which I will skip. And we will jump straight ahead into PDDL. So the planning domain definition language. So the idea behind PDDL is for you not to write C++ code, but just to describe your domain. I mean, describe your domain is you learn the PDDL syntax, which is to describe your problem, your agent, your world, and how will they interact with each other. It's also useful to benchmark planners, because now you have a standard input for the planners. And if all planners are receiving the same input, then you can compare the output in a objective way. So it was created in 1998 and developed for the first international planning competition, so that you could compare planners with each other. And it's inspired by strips and ADL. So PDDL is a milestone in planning, and it's very important. And this is how it would look like. So the syntax looks like this for the domain description. So you basically have types, predicates, and actions. So types are the entities in your world. So you have locations, you have robots, you have grippers, you have cameras, and so on. The predicates are describing the world from a semantic perspective. So you will have the fact that the robot is somewhere, the fact that a particular location is clean or dirty. And this depends obviously on your particular environment. And then you will have your operators or actions, which is what your robot can do. What are the skills of your robot? In this case, this robot has only 2 skills, so it can move and it can clean. So it's this Roomba example. And then this is the syntax on how you would describe a problem in PDDL. So basically you have the objects in the world. So here we have 1 robot, 2 locations, and then you have initial state, which is that the robot is in the room A, and both of the rooms are dirty, so they're not clean. And as a goal, you want the robot to be at location A once it has finished the task, and you want location B and location A to be clean, both to be clean. And so the elements are two files, which is domain.pdl and problem.pdl. Those two files are input to a planner or a solver, which will perform the search for you, and it will produce a plan. And then this plan you will send for execution. And so to model in PDL, what do you need? So a model in PDL is, as like I said, I mean, it's typically written by a domain expert. So you need to be an expert in robotics. And this is something that I found a bit nice, because being an expert in robotics means know a little bit of everything. So you need to know a little bit of perception, a little bit of manipulation, a little bit of navigation, and so on, so that you can effectively have a broad perspective and being able to model the entire environment and the robot on it. So what helps is, or the steps that I recommend is, first you write a storyline, and then you define your types. So what kind of entities do you want to have in your world? Then you draw the scenario and identify skills of your robot. And then you start to construct the preconditions and effects. Yeah, here are some PDL tools. So in particular, the first one is really nice. I mean, if you want to get better at PDL, the first link helps you a lot. And then you can query some examples on these two links below. So PDDL has evolved. So the language has evolved. It started with some weaknesses. Those weaknesses were identified, such as the lack of temporal constraints. So you cannot express time in PDL 1.2. And then some years later, PDL 2.1 was developed, which introduced temporal planning, durative actions, numeric fluence, and many more things. And furthermore, PDDL 2.1 was evolved into PDDL Plus, which allows basically processes, events, and many other features. The main one is events. So in PDDL 1.2 and 2.1, you cannot deal with events or unplanned things. And other task planning formalisms include, so the very basic one is strips. So everything, let's say, emanated from strips. All languages are inspired by strips. Then you have probabilistic PDL, which works in the context of an MDP. And this is nice because it allows for uncertainty between state transitions. And here we don't yet have the possibility to represent partial observability. So you don't have a POMDP, you still have a MDP. So the state is still fully observable. And it was the official language in the international planning competition in the probabilistic tracks 2004 and 2006. Another planning formalism is the HDDL. This allows you to describe problems in hierarchical task networks. It was very recently proposed by researchers from Ulm University. It's being used at the moment in the first international planning competition of hierarchical task networks this year. And this will allow to benchmark HTM planners. And yeah, another flavor, let's say another planning formalism is RDDL, which is to express POMDPs. So you can model partial observability and non-deterministic action outcome. It was used in the last international planning competition, 2018. And basically a grounded grounded riddle. It's pronounced riddle. A grounded riddle corresponds to a dynamic bias network. And let's jump into plan execution to finish the talk. So in plan execution, this is the classic execution architecture that you will have. So typically you have a planner, produces a plan, the controller executes the action that has received from the plan. In the most simple version, those actions will be executed in sequence, so one after another. If you have a better version of the controller or a better executor, then concurrent execution is possible. Then those actions will be dispatched to your robot, and the robot will respond with observation. So it will, with its sensors, it will perceive the world, and it will respond to the controller so that the controller can update the knowledge base. And this knowledge base maintenance is critical in execution, because if something goes wrong and your knowledge base is well maintained, you can just trigger replanning, and then you can recover from that failure. Yeah. So let's say in task planning, you need a complement, which is the environment representation. The environment representation is typically not part of planning, so this is a different area, but we need that area for plan execution. So environment representation is what we said earlier. So it's basically the translation between sensor data and domain symbols. And here is, for example, in the context of AMCL, you trigger localization, you know where your robot is in the environment in certain coordinates, like 5 meters and 6 meters. But symbolically, what does that mean? Are you in the kitchen? Are you in the living room? Are you in the bedroom? So you need to translate this sensor data to a symbol and store this into knowledge base. And this is the environment representation. And from the environment representation, we will fetch the knowledge to construct the PADL problem for the planner to come up with a solution. And so we have a famous framework for execution execution framework for robotics. We have ROSPlan. So ROSPlan is based on ROS, which is a robot operating system. It's based on ROS1. It's maintained by KCL University, but it has contributors also from University of Strathclyde, and we are also contributing the FKI to ROSPlan. It's open source, and some of its features is that you need to install ROSPlan from source. It supports PADL 1.2 and 2.1, so temporal actions are there. There is some initial integration of Riddle with the PROS planner. And at the moment, it does not have support for HTN, but we are working on that, and in the next months, it should be there. Concurrent action dispatch is possible via the SciRoc dispatch. And it also offers multiple GUI interface based on Qt that are very useful for debugging. And this is an overview of ROSPlan. So you have a knowledge base which stores the collection of facts that we were talking about. You have an automatic problem generator. You have a problem interface, planner interface, parsing, and plan dispatch. So what are the inputs to ROSPlan? So the inputs are PDDL domain definition. You need to have an ActionLib interface also. So your robot needs to run with ActionLib. You need to partially maintain the knowledge base of ROSPlan with sensor data. So this translation of sensor data to symbols, you also need to provide. and you need to select a planner that you want to work with. And what does ROSPlan gives you? So ROSPlan gives you a high-level control of your robot actions and nice UI interfaces, so you can keep track of the plan and that you can see the knowledge base and that you can debug all the process. So now we have some demo videos which maybe we don't have the time to do, but I think you can just see the video offline alongside with an explanation diagram of that particular demo. And the limitations of ROSPlan is that at the moment it's very tightly coupled to ROS1. So this means that migrating ROSPlan to ROS2 is not an easy and straightforward task, but we are working on that. You inherit the limitations from the formalism. So in this case, ROSPlan has limitations as PDDL 2.1, which one of the major limitations is that you have no model for action failure. And your best chance is to, like I said, to have a good knowledge-based maintenance so that you can just trigger replanning and create a new fresh problem from the knowledge base. And if you feed the planner with this new information, that you can recover from an intermediate state. And yeah, so just to finish the talk, I would like to talk about the areas of research. So researchers are working currently on heuristic search. Others are working in temporal planning. Others in hybrid planning. So how to deal with exogenous event, continuous processes, and nonlinear change. Others are trying to do splanable planning. Splanable planning is critical for interactions with humans. So we want robots to interact with humans. We want robots to be able to explain their plans. Why did they choose a particular plan, and why a plan could not be found, for instance. So this is a big challenge for explainability. And other areas of research include risk-aware planning. So you plan to minimize the risk. And also you have collaborative planning. So how to merge teams of robots with humans and how to enforce this collaboration of the two. You also have long-term autonomy and the combination of motion planning and task planning. So a plan might be different if these particular locations are very far away from each other, which this information you could only know if you perform motion planning first. And you also have the intersection between task planning and machine learning, as we previously mentioned. And these are some of the venues that I leave here for reference. So with that, and the International Planning Competition, which is organized as part of the ICAPS conference, I would like to also remark the Plan Rob workshop that it's typically organized by Dr. Michael Cashmere every year. And this is in the intersection between task planning and robotics. Yeah, so with that, I think I would like to conclude the talk. And I'll be happy now to take questions.
Thank you, Oscar, for the wonderful talk. I think there are some questions in there. But before I go to the questions, the best quote I liked from you was, "Being a robotist is to know a little about everything." I think that sums up the whole, for all you new engineers and researchers who wants to get into robotics. It's always important to have an eye on different fields, right? I think it's very important. I think this will be a quote which you can take from this talk from my. It's really interesting. So there are some questions coming. So this is the first question from Santosh. He asked, what are the drawbacks and limitations of using task planning in robotics?
So this depends on the formalism that you choose. So for example, if you go for PDL 2.1, let's say,
Okay.
What you have is deterministic action outcome. So the drawback is that from the model, from the plan assumes that your robot will always succeed when it performs an action, and this might not be true.
Okay.
Yeah.
Nice. So there is also a follow-up question to that. So are there frameworks that do allow you to model action failures? I think this is also my question in my head also. If not, what would be the right approach to incorporate failures? So my question from my experience in ROSPlan, how do you incorporate failures? Because in one of your slides, you clearly mentioned about it is deterministic, what it is not, correct? And one of the assumption is that it will work, right? So that's that it doesn't consider failures. But robotics is a field of failures. There's so much failures which occurs every time. So these are the two concepts which are not combining. So how are you handling this in this ROSPlan? How can anyone handle this?
Yeah, so the formalism that allows for non-deterministic action outcome is the PPDDL, so probabilistic PDL, and this is not supported in ROSPlan, but we have support for Riddle, and Riddle goes one step beyond, which is includes also partial observability.
Nice.
So ideally for robots, what we want to do is we want to plan in POMDP framework, in POMDP world. But of course, this is hard. So this is not easy. And this is an entire new research area on itself where researchers are developing these planners and trying to improve them. But as for now, they can only cope with very limited and small problems.
Right. The other question which I was coming in my mind was, how much time does it take? So I know that state machines are quick, at least they are good and quick. What about the time taken in making plans using PDDL based planners? How do you go with that?
Yeah, so this is actually an interesting question because the planners, if you as a roboticist want to integrate planning in your robot, you will typically go to you will want the best planner available.
Right.
But what is the best planner available? That's a tricky question.
Correct.
Because you need to benchmark the planners objectively to see which one is the best. And fortunately, there's a venue that does that for you, which is the International Planning Competition.
Right. Okay.
So in the International Planning Competition, they do the benchmark for you, and then they tell you which one is the best planner.
Okay.
And
so,
then, yeah.
Yeah, no, I was also talking about how much, let's say you have the Robocop task of pick and place, right? Pick and place robot. So how much, what is the time taken in such a situation to make a plan in such a plan? If you have a PDL or problem domain you have, with some planner view you have.
So the issue is connected to the previous question. The thing is that in the international planning competition, planners are given with a deadline of half an hour to come up with a solution.
Okay.
So this means that people from the planning community, they will make a planner, they will submit their planner to competition, and as long as they fulfill this deadline, they are fine. So they don't design planners to be fast. They design them to perform under half an hour.
Okay.
But what we need in robotics is fast planners that could come up with solutions in under a minute. And this is actually a loophole in the planning community. So there has to be researchers which specific focus is to generate fast plans. And some planners, what they do is they provide with anytime features. So at certain intervals of time, that they will give you one solution, and then they will try harder to find a better solution and a more optimized one. You will get a more refined solution in 10 minutes and a better one in 20 minutes and so on. But you can start executing the fast one, let's say, which was
Right.
a bit bad.
So I think this gives us a good opportunity, at least from the European Robotics League, that this is a good benchmark to do, right? So I think this is not important to the planning community, but this is important to us robotics community. So this is a good benchmark to be done, that we need a PDDL planner which plans faster. It's not important to have the best plan, but it gives a faster plan. I think maybe we should take this up in the robotics community. Okay.
Another thing is that it's typically a good idea to find a domain which is similar to your domain. So
Right.
in the planning competition, they are benchmarked with multiple domains, like 10 different domains,
Yeah.
and they have to be generic enough to cope with all of them.
Right.
But if a particular planner has performed particularly good in one domain, which is similar to yours, even if that planner is not the best around, but is the best for your domain,
Right.
then you can use it as a domain-specific planner.
So you're saying it just doesn't need to win the competition. They should be also towards some planners of domain specifically. So you should look into that aspect also.
Yeah.
So there
Exactly.
are some questions also coming from viewers. So there's one more question from Yusuf. He says, what is the degree of which planning is involved in robot action and task? Should the planner only consider high-level action level tasks, or the planners also responsible for low-level actions? So at what level should the planner come into picture? It's only at the higher level, or at lower level, like driver space or some to that place. So,
Yeah. So this is a design choice. So you can design this. You can choose. But in my experience, is typically a good idea to keep it at a high level and to handle the low level, possibly with a state machine.
okay, maybe I can add in a bit here, because I'm working with my fellow coordinator, because he's working with PDDL to do robot motion planning. So he's using in the controller. So there are some people even doing at control level to use PDDL as a thing. And there's one more question. The last, maybe, so it's by Jose. He's asking, are there any requirements to integrate a task planner into a software architecture? So what are the minimum requirement, and robotics should take care to integrate it into an architecture of the robotics?
By software architecture, maybe he means ROSPlan. So what are
No,
the
no.
minimum
I think
requirements?
if a robot has an architecture, so they have ROS. I think the one will be they need to run ROS. The ROS architecture, if they have in robot, what else do they need to plan to integrate a task plan?
Okay, so in particular case of ROSPlan, what you need to have is PDL 1.2 or 2.1,
Right.
or being able to support Riddle language, but that's a bit experimental. Let's say the default system is constructed to handle PDL 2.1.
Right.
So if your planner supports PDL 2.1, then it can be very easily integrated into ROSPlan.
Good. So I think with that we have reached our end of time. But before you go, I think as you know, we are running the parallel Gerhard K. Kretschmer Memorial Symposium, and I know you are a student of him. So what I would like to ask you: do you have a special memory with him which you'd like to share with us? This the smile explains a lot. A lot of it.
Yes, yes, of
So how
course.
do you what do you want to share some experience with him?
Yeah, so for me, it was actually funny because I took the planning lecture with Professor Kretschmer.
Ah, so
And
he's your more inspiration, mode of inspiration.
yeah, I mean, to me, Professor Kretschmer has been very important because thanks to him, I have a job basically.
It's very nice too. That's
Yeah.
I think he has this kind of role on many students' careers. But yeah, that's so it's nice to know that he's with this planning also he's involved with us. Good. Thank you, Oscar. I think with this, it's the correct moment. It's been 1 hour. It's been a wonderful talk. I hope that most of our fellow robotists and fellow students who wants to learn and enter the planning field, they got a brief idea about the field and what you can do. And finally, I want to again end up with the quote of Oscar that the last thing is being a robotist is to know a little bit about everything. So yes, thank you, Oscar. Thank you for the wonderful talk.
Thank you very much.
Bye bye.
Bye.
So with that, that was Oscar with us. Let me share. So before we sign off for today, I have to explain. We can give you a brief overview of what we have planned for the next 2 days. So here we go. So tomorrow, so that was Oscar Lima today. Tomorrow we continue with the SciRoc camp. And tomorrow we have the last lecture, the series in the Champion Stock series by Abhishek Padalkar. So Abhishek Padalkar was part of the Bitbots at Home team, which successfully won the Open the Door challenge in SciRoc Smart City at Milton Keynes. So in this talk, Abhishek will go through their solution and how they were able to find a proper solution to open the door and why this problem is such a complex problem. Let us also remind you, we are running the Gerhard Kretschmer Memorial Symposium, which is running parallel to the SciRoc camp. So this is the schedule. So here was today on Wednesday, we have the talk, and tomorrow. So there is an announcement in the symposium talk that the talk by Dirk Holz, which is planned at 16 Central European time, has been cancelled due to an emergency situation. But don't worry, we come tomorrow at 10. Will be joined tomorrow morning at 10 by Fernando Ribeiro. So please stay tuned for that. So with that, this is Deepul Nair signing off for today. Till we meet tomorrow.